Begin with chemical properties of nitric acid. When you talk of chemical properties of nitric acid, okay, what happens is, first is we are talking about action of nitric acid, on metals. That's the first one we are talking about. Action of nitric acid on metals. Is this clear? First metal that you can talk about is a transition metal, copper. So copper reacts with dilute HNO3. Okay. And what does it form? It forms copper nitrate, CuNO3 whole twice. So even dilute nitric acid is an oxidizing agent. It oxidizes metallic copper to copper. Plus what do you have? H2O plus nitric oxide gas. Remember, nitric oxide has a odd electron molecule. The same copper, when it reacts with concentrated nitric acid, again forms copper nitrate, CuNO3 whole twice plus H2O plus NO2 over here. Again, NO2 is an odd electron molecule. Whereas with zinc, see, zinc reacts with dilute nitric acid. Zinc reacts with dilute nitric acid to form zinc nitrate, ZnNO3 whole twice plus H2O, and here it forms nitrous oxide, N2O. Is this clear? And zinc reacts with concentrated nitric acid to form zinc nitrate plus H2O plus NO2 plus NO2. Is this point clear? There is a very odd question which sometimes is asked, that is, what happens when zinc reacts with very, very dilute nitric acid? It's 2%. Either it's very dilute nitric acid or 2%. It's a very odd question. Many textbooks have not given this. So what happens? You get zinc nitrate, no doubt, ZnNO3, plus here you will get ammonium nitrate plus H2. So here this is a case of, you have to remember this. So always read the question carefully. Just dilute, or sometimes they say very, very dilute, or they give you the percentage 2%. Is this point clear? Action on non-metals. We are still on chemical properties. Action on non-metals. So when you're talking of non-metals, we have carbon. So carbon, when you react it with concentrated hot nitric acid, HNO3, what happens is we get carbon dioxide plus NO2 plus H2. Okay. But with sulfur, what happens is sulfur reacts with concentrated nitric acid and it oxidizes it to sulfuric acid, H2SO4 plus NO2 plus H2. It oxidizes iodine. Okay. Iodine is I2. Concentrated nitric acid oxidizes iodine to HiO3, iodic acid, plus NO2 plus H2O. Then we have phosphorus. Concentrated nitric acid oxidizes phosphorus to phosphoric acid, H3PO4 plus NO2 plus H2O. This is on action on noble metals. Action on noble metals. See, what happens is aqua regia is a mixture of HNO3 and HCl in 1:3 parts. So what happens is HCl plus HNO3 forms NOCl plus H2O plus Cl, NOCl plus H2O plus chlorine. So what happens is gold reacts with this chlorine, the reactive nascent chlorine, and you get, of course, in presence of HCl, so you get HAuCl4, HAuCl4, that is auric chloride. Auric chloride, is this clear? Or orochloric acid, auric chloride. It can also be, you can say it is orochloric acid. So what happens? This dissolves. This is how gold is dissolved. Similarly, platinum reacts with this nascent chlorine. And what does it form in presence of HCl? It forms H2P2, H2PCl6. It forms H2PtCl6. That is hydroplatinic acid. Hydroplatinic. So what happens is that these are soluble compounds. This is how gold dissolves. So how do you recover the gold? Simple idea. To this, if suppose we dissolve gold, once it becomes orochloric acid, simply by adding urea, you can regenerate the gold. So this is what the jewelers do. They dissolve it in aqua regia, okay, remove the other impurities, and then they add urea and remove what you call the gold back. Repress about brown ring test. Actually, this is a part of your qualitative analysis of your 11th and 12th test for nitrate. Okay. See, what happens is that how do we go about doing the test? So we'll understand and then look at the theory part of it. See, we suppose we have nitrate, NO3 minus. This is clear. Then we add sulfuric acid to that. Okay. After we add sulfuric acid to that, what happens? We add freshly prepared, what you call ferrous sulfate. Freshly prepared ferrous sulfate. Is this clear? And if there is nitrate, what happens? We get a brown ring at the corners. This has to be carefully added because what happens? If you shake a little, then the brown ring gets disturbed and the solution becomes colorless. So what is the funda behind it? See, what happens is nitrate is reduced to nitric oxide and ferrous is oxidized to ferric oxide. So it's a redox reaction. Ferrous is oxidized to ferric and nitrate is reduced to nitric oxide. So this is the first part. Then the remaining we have added freshly prepared, what do you call? We have added sulfuric acid. So sulfuric acid, then what happens is, in the acidic, then what happens is, the remaining freshly prepared ferrous sulfate is basically FeH2O6SO4. Is this clear? Now here, this nitric oxide formed over here gets added and what happens? We get FeH2ONO plus. That is, now here, this is a brown ring complex. Now here you have to understand, when the question is asked, what is the kind of question? So FeH2O5 is penta-aquo-nitrito iron 2, whatever it is clear. Now here the question that they ask in entrance exam is, what will be the charge on Fe? See, when it is a brown complex, what has happened is, see, we have Fe, H2O5, NO plus. So this plus 2 is because this is Fe plus 1. So what has happened is, nitric oxide, I have been repeatedly telling you, it is an odd electron molecule. So there is a transference of electron from here to here. So here the name will be what? Penta-aquo-nitrosonium. Penta-aquo-nitrosonium iron 2. Iron. Is this point clear? But the moment you shake it, this electron which it got is returned back and in a colorless complex. In a colorless complex, what is going to happen? Now here Fe will have a charge of plus 2, H2O5, NO plus 2. So here it will be penta-aquo-nitrito pentaaconitritol. Here it was nitrosonium because plus nitrito Fe in the brackets, parenthesis 2. Here parenthesis will be 1. Are you understanding? So when in the entrance exam they ask question, what is the oxidation state of Fe in the brown complex? Then be very clear, it is Fe is having a charge of +1 because of transference of electron. Is this point clear? So this is why this is very important from the examination point of view. Is this clear? I have not written down the name because I think we have taught this in coordination complexes. Okay? So this becomes nitrosonium and this becomes nitronium actually. Then we come to uses of nitric acid. What is there to talk about uses? The country's GDP is calculated by the amount of sulfuric acid and what you call nitric acid used. Mainly used for making what? Fertilizers. Mainly used for making fertilizers. TNT, trinitrotoluene explosive. Okay, used for making aqua regia, which is used to dissolve noble metals like gold and used as an oxidizing agent in organic chemistry. Oxidizing and nitrating agent in organic chemistry. We now talk about oxides of nitrogen. The first one we talk about is nitrous oxide or dinitrogen oxide. The formula is N2O. So here the oxidation state is, you can see O -2, so balance. So nitrogen has an oxidation state of +1. The simplest commercial method of preparation is what? We take ammonium nitrate, okay, and just heat it. So just slow combustion of ammonium nitrate, when you heat, you get N2O plus H2O. N2O plus H2O. So when you talk of nitrous, it is a colorless gas. It is a colorless gas, sweet smell. So when we talk about the structure of nitrous oxide, okay, when you talk about structure of nitrous oxide, what happens is, it has N triple bond O, the resonating hybrid is between N double bond N, N triple bond N, N double bond, N double bond O. Is this point clear? So what happens over here is N double bond, N double bond. So there can be a question which can be asked. In which oxide of nitrogen it has a N triple bond N? You know, one of the local entrance exam, they ask this question because if you look at all the oxides that we are going to learn today, it's only nitrous oxide that one of the resonating hybrid has a N triple bond N structure. See, the most important thing is when you talk of nitrous oxide and the other one, next one, nitric oxide. See, these are the only two oxides which are neutral in nature. These are the only two which are neutral in nature. Whereas what happens is, the all others, whatever I'm going to talk about, are acidic in nature. So that's one more thing as a property you have to remember. Which oxide of nitrogen is, what do you call? Which oxide of nitrogen is neutral? So nitric oxide, you know that nitric oxide has it's an odd electron molecule. See, oxygen has a charge of -2, so nitrogen has a charge of +2. One of the methods of preparation is simple. There are many methods. One is what we have already been studying, action of nitric acid on metal. When you treat copper with nitric acid, it forms copper nitrate H2O plus nitric oxide. Is this clear? You can't use zinc because zinc forms nitrous oxide. Okay, it's a colorless gas. It exists in a resonating structure N double bond O, where it has a charge of plus and minus. Is this point clear? And that will be N double bond O. Now what happens is, one thing from the examination point of view, very important that we have to know is two things here. Nitric oxide is the only one which can act as both oxidizing as well as reducing agent. So this is one point. Then the positive part, NO, when it loses an electron, NO, nitrosonium ion, is isoelectronic. So this is from the examination point of view. Is isoelectronic with nitrogen gas. Are you understanding? So this is some tidbits which I am teaching you, which you have to remember from the examination point of view. Is this clear? That, see, when we talk of oxidizing and reducing, very few substances can act as both oxidizing and reducing agent. We have hydrogen peroxide, sulfur dioxide, and sulfur dioxide. Hydrogen peroxide, sulfur dioxide, nitrous acid, nitric oxide, and nitrous acid and ozone. So these are 5 compounds which can act as both oxidizing as well as reducing agent. And this is what is asked in the exam. Identify the compound which can act as oxidizing as well as reducing agent. Is this point clear? Talk about dinitrogen trioxide, also called as nitrogen 3 oxide. From the entrance exam point of view, which is also called as anhydride of nitrous acid. As you can see, 2x minus 6 is equal to 0, so oxidation state is plus 3. See, what happens is, how is it prepared? It is prepared by mixing nitric oxide with N2O4. Understand the temperature, it is minus 23 degrees centigrade. So around minus 20, 250 Kelvin, 273 is 0. So 250 Kelvin is minus 23 degrees centigrade. It forms N2O3. Is this clear? It is passed through NaOH and to remove the other impurities. And what happens is, then you get a blue solid. So this is a blue solid and a pale blue liquid. Is this clear? So this is a question which you should remember, that N2O3, which oxide of nitrogen is blue in color? So in the solid state it is blue solid and pale blue liquid and colorless in gaseous state. So what happens is, as far as the structure is concerned, it exists as 2 resonating structure. This part of the structure, it is planar, whereas this oxygen is outside, and that makes it non-planar. So part of it is planar. So N double bond NO is in one plane and this NO is in another plane. Is this point clear? So in the 3-dimensional structure, partly it is planar and partly it is out of plane. Okay. So, and as I told you, except N2O and NO, all others are going to be acidic in nature. Dioxide again is a molecular formula NO2. It has an odd electron molecule. It is highly reactive and mostly it exists in equilibrium with N2O4, which is the next oxide we are going to talk about. So at low temperature, practically it exists as a dimer. Is this clear? At about 100 degrees centigrade, it decomposes to form a brown colored gas. Is this clear? Oxidation state of, so since I will be discussing this in the next one, I am removing it, but for your knowledge you must know that at a lower temperature it prefers to remain as a dimer. Is this clear? Then oxidation state is plus 4. Simple heating of lead nitrate. Just heat lead nitrate, it forms lead oxide plus NO2 plus oxygen. Is this clear? And NO2 itself, if it decomposes, what happens? NO2 decomposes to form NO plus O2. So one of the properties, brown gas, it acts as an oxidizing agent. It acts as an oxidizing agent. So NO2, if suppose there is sulfur and NO2 gas, if you heat it, NO2 will support the combustion of sulfur to sulfur dioxide. Is this clear? So that is an example where it acts as an oxidizing agent. When you look at the structure of, these are the two resonating structures of nitric acid. They are planar but angular. So among the oxides that you saw, only N2O3, is this clear, will be an example where it is non-planar, partly planar and partly non-planar. Is this, as I told you, dinitrogen tetraoxide. Basically it is nitrogen dioxide which exists as dimer. As you can see over here, nitrogen dioxide, if you cool it to a temperature of minus 10 degrees centigrade, it forms dinitrogen tetraoxide. And dinitrogen tetraoxide, when you heat at around 100 degrees Celsius, 90% is complete, 140 total disintegration takes place, decomposition takes place to form NO2. It's a colorless solid. Now here you can see N2O4 is a planar molecule, and these are the two resonating hybrids. Can you see over here, the double bond is over here with these two oxygen, and here, like how we say cis and trans in organic, it's not the correct representation. There is no cis and trans in inorganic chemistry, but something like that. They are on the same side, whereas here the double bond is on the opposite side, but the molecule is planar. It's very important, because I told you only this molecule is non-planar. All other oxides of nitrogen are planar. So that becomes a scope to ask for what you call N2O3 will be non-planar. That gives a scope for asking a multiple choice question. Nitrogen pentaoxide. Dinitrogen pentaoxide is also called as anhydride of nitric acid. It's basically prepared that way. It is prepared by heating nitric acid over phosphorus pentaoxide, which is a dehydrating agent. You get metaphosphoric acid and N2O5. It's in the gaseous state, it's colorless gas. In the solid, it's a colorless ionic liquid. So in the gaseous state, it has a structure like this, whereas in the solid state, it is ionic, and it's called as nitronium nitrate. So NO2 plus. See, NO2 plus is isoelectronic with carbon dioxide. So NO2 plus and NO3 minus is nitronium nitrate. Is this clear? So this is all that we have about oxides of nitrogen. We can always add over here that NO, I missed it, nitric oxide also exists as a dimer. Okay. So this is how it can exist as a dimer. Okay, I forgot it. And then, so this is about